Hello Physics, Part 2, maybe 10 more minutes, and you're going to be an energy expert. Energy skate park, you did it. If this guy, and I'm just going to make easy numbers, if he had 16 joules, now he's probably going to have way more because, maybe, here, let's do a regular number. Let's say he's 60 kg. I'm going to just calculate how much potential up here. He's on Earth, and let's say that ramp is 2 meters tall. 600, so we're looking at 1,200 joules. That's not a bad number. It's all potential. Down here, he is at height equals 0. OJ, so the kinetic must be 1,200 joules. Energy is conserved. Of course, this isn't a perfect world with no friction. Let's do the bowling ball. Let's say the bowling ball, I lift it up 1 meter above the start, or above its low point. Remember, the ground is down here. I'm just going to call this, even though it's not the ground, its height equals 0, because heck, the floor of the classroom is actually not the green grass ground level, and the green grass ground level outside is not sea level. So pick height equals 0, you get to pick. Make it easy. Alright, let's go. So 1 meter there, bowling ball is maybe 5 kilos. So, pause the video and calculate the GPE up there. Go. By the way, I'm making all the math in your head math. It should equal mgh, and by my eye, that looks like 50 joules. Okay, now we saw this bowling ball in class, and we saw that it's a pretty efficient system. If you hold this to your nose and let it go, it more or less comes back to your nose. Okay, so down here, since all the GPE is gone, there's no more math involved, the kinetic energy should be 50 joules. Now in reality, because of some friction, maybe it's 49, and then it gets up to here, it's 48, 47, 46 joules. That's why you don't get hit in the nose if you let it kiss your nose to start and let go. Okay? That's it. Hot Wheels car, I hope you're seeing the theme. Hot Wheels car, maybe it's 0.16 joules. Okay? Because you did the math in lab, you massed it, you measured the height, maybe you let it go from 30 centimeters. I don't know, you actually tested a couple of heights. Okay? So down here, because it has OJ on the potential energy, it should have 0.16 joules down here, but it doesn't. Maybe it has only 0.12 joules because it's 75% efficient. So the other 0.04 joules was, and I'm going to say lost, energy doesn't disappear. But when it turns into heat, like friction, it's very hard to measure, so we say it's lost. That's that 25%. Okay? So energy doesn't disappear, but we do lose some mechanical energy. Just be careful that you understand what it means by lose energy. Okay? So, when I look at problem set 2, well, let me back up. You're going to see some efficiency questions on the quiz, okay? This is not, the author hasn't really done problems like this, but we did it in lab. You did 3 efficiency calculations for your car in lab, right? 3 different heights at least, okay? So make sure you can relate these energies, right? Given any 2 of these, given these, what's the efficiency? Given this, how much energy are you going to see at the end? Given this, how much did you start with? Make sure you can do that. Okay? Last but not least. Okay, no, not last but not least. Next, when you look at the homework problems, okay, let's look at some of the homework problems. Alright, so Problem 31, they tell you that, hey, this bow and arrow has 50 joules of elastic energy. And you say, whoa, Mr. Norton, we didn't talk elastic energy. And they basically say, hey, assume that it's all converted to kinetic. How much kinetic energy does the arrow have at the end? Well, if there was 50 joules of energy to start, you tell me how much energy is left at the end. Okay? I'll put the answers to this homework up tomorrow. 55, problem 55. I'm just kind of going through here. You're hoisting a sack of grain. They give you the weight and the height, how much work, force and displacement. What's the increase in potential energy? Well, that's going to be, remember the notes, work done will be the change in energy. And then they say, oh no, the rope breaks and it falls to the ground. What will be the kinetic energy the sack has right before it hits the ground? Just like the Hot Wheels car, just like the bowling ball, just like the skateboard. If you know how much GPE it has up high, you know how much KE it will have at the bottom. Okay? And so you got some problems like that. There are some problems, okay? I'm looking at 56 part C, I'm looking at 58, I'm looking at 65, so you probably want to be able to do this as well. And you did it in the Hot Wheels lab also. But there are some situations where you know the energy. It's not like, hey, what's the energy at the bottom? And you're trying to find the speed, okay? So a problem like 56 part C, we've already figured out that there's going to be 20,000 joules of energy that the system has. And so they say, what is the speed? Okay, at the end. So you have to do the algebra, and you see that it's speed squared, so you're going to have to do some algebra, and this actually isn't that bad. A half of 20 is 10, and you divide both sides by 10, and so it's going to be the square root of 2,000, and that's not so bad, okay? Make sure that if you're given the energy, you can kind of undo it and go backwards to get speed, okay? That's like the other thing going on. If you got to the half projectile portion of the Hot Wheels lab, you did this, actually. Okay, you had to figure out the speed it had at the bottom of the ramp. Alright, lastly, I got just a couple minutes left. I want to keep it to under 10. So, lastly, this is going to be on the quiz. Things like this. What if you have a roller coaster? And there's all these points. Folks, this is Hot Wheels. This is a very big Hot Wheels lab. This is a very fancy kid on a skateboard. Okay? It's still energy conservation. Absolutely, positively. So if you can figure out the MGH up here, and let's say it's like, 500,000 joules. Okay. How about this? If GPE here is 300,000, you tell me what's KE? Well, the total's got to be 500,000, folks. So 200, I'm going to be fancy, kilojoules. That means 1,000. 200,000. Okay. Point D is just a little, how about down here? Well, the GPE is 0. So the KE would be what? Well, system has 500,000 joules, so it's still got to have 500,000 joules. Now, usually when you're dealing with a fancy problem like this, real world, you know what a roller coaster does. There's friction. There's air resistance. There's all this stuff. Okay? But when you're dealing with a fancy problem like this, usually the author will keep it such that, hey, friction is non-existent. Okay? Or maybe they say, they wanted to get super fancy, maybe they would say, oh no, there's only 400,000 joules here. How much work was done by friction? Well, you know there should be 500,000 joules of energy accounted for, so you've got 100,000 there. Okay? But that would be one situation. And you can figure that out any place. Let's go back to the no friction example. Let's say, no, let's keep it friction. Let's say here, the GPE is, well, it looks like it's a little higher than that, right? So let's just call it 310,000 joules. And let's say the work done by friction, as it did all of this, is now up to 150,000 joules, right? And then I would say, what's the kinetic? Well, you know the total has to be what? 500,000 joules. So we're at what are we at? 460? So 40,000 joules. Thankfully, it's still moving, so it might, hopefully, we'll make it through without falling off the track. But this right here is the kind of, really, the ultimate understanding. Why do we lift pulleys? Why do we roll Hot Wheels cars? Why do we put bowling balls to our nose and let go? Why do we do energy skate park? To understand the engineering of these kinds of things. Okay? Of course, if you know this, you could figure out the speed here. You could figure out the speed here. You could figure out the speed here by taking at any one of those spots, right? The KE at D would be 1/2 mass speed at D squared. You know that. You'd be given the mass of the train or the person in the train, and you could solve for that. Hey, I went a little over, but good stuff. Okay. So we got a couple days off. Man, hunker down at some point. Work on this. You can do it. Peace.